Welcome, and thank you for coming. Today I'd like to talk about the birth and amazing life of nonlinear optics. About 58 years ago, in the summer of 1961, a truly amazing event occurred in Randall Lab just across the way. For the first time ever, this group of Peter Franken, Alan Hill, Wilbur Peters, and Gabriel Weinreich observed the frequency doubling of light. So light came in at one frequency and came out at twice the frequency. Or it came in at one wavelength and came out at 1/2 the wavelength. So it's almost like this. Let's play this. It's like you hit this note, which is middle A, and you heard a higher pitch. So middle A is 440 hertz, but then out comes twice the frequency. Now that is amazing. Now, in order for that to happen with light, you need very intense light. So this incredible event needed the development of the laser. The laser is the source that can produce enough intensity for you to be able to do these amazing things. Now, it was quite revolutionary. Oops. Come on. Come on, advance. Okay. So nonlinear optics requires very high intensities, and at those intensities you generate harmonics, light waves can interact with each other, the refractive index becomes dependent on intensity, the light beam can even focus upon itself, even without a lens. Now, Peter Franken, whose idea it was and who led the experiment, tells us why it was so revolutionary. At that time, everyone was thinking about light as photons. You know, these particles quantized with definite energies, the energy proportional to the frequency. They were all thinking about photons, and you can't change the frequency of a photon. And so it was revolutionary that he came up with the idea that you could have optical harmonics. Now, to show you how much people doubted that possibility, Willis Lamb, no slouch himself in optics, he won the Nobel Prize for Physics in 1955, he bet Franken a nickel when he came to visit Michigan in 1961. He bet him a nickel that he couldn't double the frequency of light. He told him to stop wasting his time, you know, as Franken was laboring to double the frequency of light. He said, stop wasting your time. You're never going to be able to do that. So he bet him a nickel. So at the time, you bet a nickel if it was a really, really important challenge. So that was the sacred bet. If it wasn't so important, you bet $5. So that was the vulgar bet, yeah? Now, I mentioned that nonlinear optics needed the development of the laser. Now I'm going to tell you some of the circumstances that led to that event happening right here at Michigan. So, in 1959, Peter Franken organized the very first Arbor conference on optical pumping. That was in June 59. Optical pumping is a process where you use intense light to elevate electrons to higher states so that they can eventually fall down and you get laser action or maser action. So it was at that conference that the first public use of the word laser occurred. And that was by Gordon Gould. Gordon Gould coined the term laser. And laser is an acronym. It stands for light amplification by stimulated emission of radiation. So we should be, this is really historic that the first use of that word was right here in Ann Arbor. Well, less than a year after that conference, Ted Mayman, working at Hughes Research Labs in Malibu, California, created the first working laser. There were tons of people in a race to make a laser, but Mayman beat them all. He made the ruby laser. So he sent out a paper to FISREV Letters, and FISREV Letters rejected the paper, claiming, well, this is just another maser. The maser, the microwave equivalent and precursor of the laser. And so the editor was Sam Houseman, who he had been a professor at U of M. He's the one who came up with the concept of the electron spin. He and Uhlenbeck came up with that concept. In fact, Houseman was nominated at least 48 times for the Nobel Prize, and it's a mystery that he never won. But anyway, he was the editor, and he turned down the paper, and Franken wrote to him and said, Sam, you've got to publish this. This is really, really important stuff. But he overruled him. Okay, so shortly after the laser was invented and demonstrated, the very first commercial laser company was formed in Ann Arbor. It was called Trion Instruments. Now, there's another company, Spectra Physics, who might dispute that, but I think they were virtually simultaneous occurrences. So the very first laser company was formed here. And Peter Franken happened to consult for that company. So as a result of that relationship, he was able to borrow the laser he needed for this experiment. There were very few lasers in the country at the time. This is March 1961. And so we're lucky to have one here. Now, with those lasers, at the time, and this is a picture from 62 from Trion Instruments, they loved to use lasers to blow holes in things like razor blades. And they measured the power of a laser by how many razor blades it could blow holes through. Yeah? So here we have a 2 Gillette razor blade laser. Yeah? Okay. Really hefty. Yeah? So that was the state of the art at the time. So now, how did Franken come up with this idea for doubling the frequency of light? So Franken said, well, enough with this photon thing. Light is a wave, we all know that. It can be a wave or a particle. But he attended this Optical Society of America meeting on lasers in Pittsburgh. And during some of the talks, he started scribbling on the back of an envelope. He estimated that the focused laser beam would yield very high electric fields on the order of 10 to the 5th volts per centimeter. And that's just a few orders of magnitude away from the electric field that binds the electron to the nucleus. And so with those strong fields, he thought perhaps something interesting would happen. So at this point, I'll pause the history and we'll review a little bit of the physics so that we can understand the experiment. Okay, so light is a wave. We describe it by, it has electric and magnetic fields that oscillate. The separation between these two peaks is the wavelength of the light. Now, the light is traveling. Here it's traveling along x. The frequency is the rate at which peaks pass by, over here, cycles per second. We will often use the angular frequency, omega, which is 2 pi times l. Okay. Frequency and wavelength are related by the speed of light. Okay. So if I double the frequency, I will have the wavelength. They're inversely related. Now, light is part of the electromagnetic spectrum, which ranges from all the way from radio waves to gamma rays. Franken's experiment was around here, where he took a laser, which was in the red, doubled its frequency into the ultraviolet. All right, so now we know all about light. Let's now talk about matter. How does light interact with matter? So, matter, imagine an atom. In the absence of an electric field, we have a positive charge surrounded by an equal negative charge of electrons. And everything is symmetric, it's neutral. Now, if I apply an electric field, it pulls the electrons away a little bit from the nucleus. It creates what's called a dipole moment. Okay? So how much you've been able to displace the electron from the nucleus. Now, this dipole will create a new field shown in those dotted lines, and that new field can change the total field that's in the vicinity of the atom. Okay, so now let's put a whole bunch of atoms together, and those little dipole moments all add up to create a big polarization vector, P. Now suppose instead of a static electric field, we send in a wave. So a light wave shown in red travels through the matter, and it polarizes the material in this periodic fashion. It's like there's a wave of polarization that's going through. So I'd like us to demonstrate this wave of polarization. Okay. So we're going to do the wave. To prepare you for the game against Notre Dame tonight, show you how the polarization wave propagates. So, with my, okay, everybody ready?
Ready? And go like this, ready?
Okay.
Start here. 1, 2, 3, go. Now let's come back. Ready? Go.
Okay. So there's a polarization wave that just passed back and forth through the auditorium. Now, this polarization wave can then radiate another light wave. Now, if the light wave is not too strong, the polarization wave is directly proportional to the electric field of the light wave, and so it will radiate the same frequency of light that excited the wave, the same frequency, okay? Now, if the light is stronger, then the polarization will not be directly proportional to the light wave, and so interesting things will happen. Okay, so let me just briefly remind you of a linear relationship, linear and nonlinear relationship. So, a linear relationship, Hooke's law. We can often think of the atom as an electron on a spring. So here's an electron the spring. So if I apply a force, I extend the spring. If the force is not too strong, the relationship between force and extension is linear, like that. If it gets too strong, you might imagine that at some point this linearity will fail. Okay? Also, you notice that it's oscillating. When a light wave excites an atom, it causes the electron to begin to oscillate. And that's what leads to radiation. Okay, so I'll quickly fly through linear optics. The relationship between the polarization and the electric field is linear. I've written down an equation. There'll be a few equations in this lecture. So that quantity, chi, labeled over there, that's known as the susceptibility. It tells us how susceptible the material is to being stretched by the electric field. And that susceptibility is related to various things like the refractive index, N, of light. And that refractive index tells us how light is slowed down and how light bends when it travels through material. Furthermore, in linear optics, sending light, one frequency comes out, same frequency. Light waves do not interact in linear optics. So, you know all the stuff. Now, let's go to nonlinear optics, which is what you came here for. In nonlinear optics, the relationship between the polarization and the electric field is not linear, okay? So, we can now write the polarization as a linear term proportional to the electric field and higher order terms, terms proportional to electric field squared, electric field cubed, and so on. Okay? Those terms become important when the electric field is strong. We will look at these terms one by one. First, let's look at the second order term, the term proportional to E squared. So that's the second order polarization. And see what kind of phenomena it predicts. And this is where the little mathematics comes along, okay? So, suppose we send in light, which is oscillating at cosine omega t. Let's call omega the fundamental frequency. If you square that, you're going to get cosine squared omega t. Now, Peter Franken, while he was sitting at that conference in Pittsburgh, took out his paper and he worked out the fact that cosine squared omega t is equal to 1/2 into 1 plus cos 2 omega t. Some people remember that from high school. But let's see what this predicts. If you look at this expression, you see a 2 omega t, whereas you only sent in an omega. That's a second harmonic. So that's what leads to second harmonic generation. There's that 1 there, which has no frequency attached to it. We will see that that leads to optical rectification. So you send in light at frequency omega, and you get out a DC field. Okay? So, moving on. These things can also happen in acoustics. So, imagine a loudspeaker. So the loudspeaker, think of it as, this vibrating thing. The suspension is like a spring. So we're going to do a demo where if we drive this loudspeaker with enough force, we will generate acoustic second harmonics. So, Monica, let's generate some acoustic harmonics. You wouldn't go deaf. No. Okay, so start out at low. You only So what you've seen is a spectrum. It tells you the frequencies that are, okay, so here we have just one. That's the fundamental. And as you crank it up, you get harmonics. New frequencies are generated. So that's the result of nonlinearity. Okay? And you can generate even higher harmonics, but we'll stop there for now. Okay, you're all good there. I couldn't do the experiment with light here because I would need powerful lasers, and we're not allowed to do that. The infrared laser that I would use would have to be completely enclosed. But anyway, I think the acoustic demonstration is convincing enough. Okay. So, one other small thing to mention. In order to generate second harmonics, you need a material, a medium that is non-centrosymmetric. That is, it should lack invergent symmetry. It should look different when you flip it upside down. So here's a non-centrosymmetric medium. Here's a centrosymmetric medium. Centrosymmetric, you can see that if I take that and flip it down, it looks the same. If I flip it this way, it looks the same. Now, for those who are interested, just a quick explanation for why you need non-central symmetry. So, if I take the electric field oscillating symmetrically like this, up, down, completely symmetric. If I square it to get the second order polarization, it's only pointing up, right? There's no down. So there's no way, if it's a symmetric medium, there's no way you can tell which way is up or down. But here, if it's asymmetric, it has the proper asymmetry so that up looks different from down. And so you need an asymmetric medium. Okay, so back to Ann Arbor. Franken shared the idea with his colleagues, Gabby Weinreich and Wilbur Peters. And Weinreich pointed out the need for non-centrosymmetric crystals. And they recruited Alan Hill, a precocious U of M physics undergrad, to do the experiment. And here's the experiment. So we took a ruby laser, sent it through quartz crystal. Oh, there's the crystal, yeah. And out came both the ruby laser light and a faint second harmonic, which they dispersed the two beams with a prism and photographed the output on a photographic plate. So here's their first result. So the very big black spot there is the fundamental, the ruby laser frequency or the wavelength here. This tiny dot is the frequency doubled or wavelength halved output. At the time, it wasn't very impressive a result. So, but it was there. They submitted the paper to physical review letters, and an overzealous editor, seeing that dot and thinking it was a speck of dust, erased the evidence. So the second harmonic was supposed to be here. So this was the greatest experimental result never seen. So, the reason why their output was so weak was because this thing called phase matching did not occur in their experiment. So now, a bit more physics. What is phase matching? So let me go to here. So there's your fundamental wave, your red light. There's the polarization wave that you all did, at the second harmonic, and there's the generated second harmonic light. For maximum efficiency, they must all march together in phase. Okay? So if they are not in phase, they'll be slipping back and forth, and energy will go back from the second harmonic to the fundamental, and you will get things like this. So if you see these two waves traveling past each other, periodically they cancel each other out. You get a flat line near the bottom. Periodically, they add up. Okay? So you want to get all the waves marching in step. But there's this little problem called dispersion. Dispersion tells us that the refractive index is different for different wavelengths. Remember, refractive index determines how fast a wave travels. And that speed is going to depend on the frequency of the light. And so the red and the blue waves will have different speeds because they have different refractive indices. And so you would never get them to march together in step if you only had one kind of refractive index in the medium. Well, fortunately, there are certain crystals known as birefringent crystals that have two, but not one, two refractive indices. And those refractive indices will depend on direction of propagation. They will also depend on frequency. So here's a birefringent crystal. If I send in light, and now I'm going to use the word polarization in a different sense. Polarization refers to the direction in which the electric field vector is oscillating. Okay? So I have light coming in, that's unpolarized. I have vectors going up and down vertically, others going horizontally. When I send it through this birefringent crystal, they'll come out in different directions. So we call that double refraction. The one that's coming out polarized vertically, the other coming out horizontally. And there's an angle between them. I'm going to see if we can demonstrate this. So over here, we have an overhead projector. And I have a crystal of calcite, which exhibits this double refraction phenomenon. I'm going to place it on here. And you see two images of that P. Two images for the price of one. Now, let's see what happens if I rotate this crystal. You see one of the P's is rotating with a crystal. The other one stays fixed. So the one that stays fixed is called the ordinary wave. The one that rotates with the crystal is called the extraordinary wave. Yeah, it's very extraordinary kind of behavior. Yeah? And that means that its refractive index depends on direction of propagation for the extraordinary wave. Now, these two are polarized orthogonally to each other. How can we tell that? How can we determine that they are polarized orthogonally or at right angles to each other? Any suggestions? How do we show that they are orthogonal? Yes? Polarizing film. Good. We have one here. So I'll put a polarizing film in here. And you see one of the waves goes away because it's being blocked by the polarizer. If I rotate 90 degrees away, the other one shows up. See? There. Isn't that cool? Okay, so we have two refractive indices, And that depends on the direction in which the wave is propagating. We have normal and ordinary and extraordinary indices. All right. So how do we use this phenomenon to achieve phase matching? So let's say the ordinary wave, the refractive index doesn't depend on the direction, so it's really a circle. For the extraordinary wave, the refractive index depends on direction, and so it will be like an ellipse. Now, if I pick my angle properly, you'll see that at this angle, if I'm traveling in that direction, the refractive indices of the ordinary wave for the blue light and the refractive index of the extraordinary wave for the red light are the same. So if I want to get them all to march in step, I should align my crystal in that direction with respect to the optical axis. Okay, so another way to see that is, here's refractive index versus frequency. If my red light travels at an extraordinary wave with this index, NE, the generated blue light travels with this index N0. You can see that they are equal. So with that, let's see some actual experiments. So this is second harmonic generation, and we're looking at the light that's generated, that green light. So when you far from phase matching, because the harmonic and the fundamental are not in step, you get these interferences, and the intensity doesn't grow very large for the second harmonic. As we get closer and closer to the correct angle, you see that the intensity gets higher, there are fewer interferences, and eventually when you hit exactly the phase matching angle, there will be no oscillations, and the generated second harmonic will just keep growing and growing. So based on this phase matching idea, the efficiency of second harmonic generation grew by leaps and bounds over the years, to the point that we can now actually have nonlinear optics going on in this laser pointer that I'm holding in my hand. Okay, so let's do some surgery on this laser pointer to see what's inside. So my green laser pointer, I moved too fast. Green laser pointer, if you split it open, you will see that there is this laser here, which is a solid-state laser, neodymium terbium vanadate laser, putting out a wavelength of 1064 nanometers, which is in the infrared. Over here is a crystal, a nonlinear crystal called KTP, and that crystal doubles the infrared light frequency, and now it comes green light at 532 nanometers. So now you can actually buy on eBay and Amazon a nonlinear optics device. You can hold it in the palm of your hand. Now, some of the cheapest laser pointers do not have an infrared filter to block out the infrared. And so it's not a good thing. You don't know that a whole lot of infrared is coming out from there, in addition to the green. And also, you should never ever point these laser pointers, at people or at aircraft or anything like that. You can go to prison for pointing at an aircraft. Okay. So another application that we're really, really proud of It's the Hercules laser right here at the University of Michigan. Now, the Hercules laser has set the Guinness Book of World Records record for the highest focus intensity in the world. Now, this laser relies on nonlinear optics. Oh, let me introduce my colleagues. There's John Nees and Tolia Maxenchuk, great laser engineers who do the care and feeding of Hercules. All the green light you see in here is from frequency doubled lasers. Okay? It's very hard to make a green laser itself with the kind of efficiency we need. And so all this green is from nonlinear optics. You double the frequency of infrared, and you get that. Now, let me tell you a bit about the intensity. So it puts out, when focused, 10 to the 22 watts per square centimeter. Actually, 2 times 10 to the 22 watts per square centimeter. That's equivalent to focusing all the light from the sun that hits the earth and focusing it down onto a grain of sand. Imagine that. To focus all the light that hits the earth and focus it down onto a grain of sand, that would be the equivalent of the Hercules laser focused down. Okay, so this is a pretty powerful beast. Okay. Well, this goes a bit more into the, there's a block diagram that shows you the amount of nonlinear optics in the Hercules. All these green boxes are frequency doubled pump lasers that pump what's known as Ti-sapphire amplifiers over here. In fact, one of these is putting out like 40 joules of second harmonic. Over here is the oscillator that puts out short pulses, and we'll talk about that also shortly. It's based on something called Kerr-Lens mode locking, which is another nonlinear optical effect. Second harmonic generation has also found application in biological imaging. So here you see imaging of collagen fibers. Now, I had mentioned that for second harmonic generation, you need non-centrosymmetric materials. Well, it turns out that the collagen fibers, which are these elongated fibers, they are non-centrosymmetric. And so you can actually generate second harmonics by shining infrared light into the tissue. The tissue begins to glow green. So it's very important that you can do that because now you don't have to stain the biological sample. The color just comes naturally from the harmonic generation. And it also has very good resolution because you have to focus the light down to a very small spot to get enough intensity to generate high harmonic. Okay? So I understand that it's already making its way into the operating room. This is from an article I saw recently. Okay, so we've seen the second harmonic. The other quantity in that expansion of cosine squared was the 1 which represents optical rectification, where you send in light at optical frequency through a crystal, and it generates a DC polarization, a voltage across the crystal from sending in light. Now, since we use intense pulses, the envelope here is not going to be really constant. And so if you send in, we'd have to send in something like a pulse, and optical rectification will extract the envelope of the pulse. So Franken, Bass, and co-workers demonstrated this also in 1962. Terahertz radiation is at a frequency of 10 to the 12 or thereabout, and it has important applications. One of them is scanning. So, there are terahertz scanners which act like X-rays, but are better than X-rays because they are non-ionizing, and so there's no risk of developing, tumors and things after repeated exposures. And in an application that was pioneered also here by Professor Muru and some of his graduate students, terahertz radiation has been used at the Louvre to examine art. So here, there's Bianca Jackson, who she was a graduate student here. She spent some time at the Louvre and used terahertz radiation to discover that an old fresco in their collection had underneath the top visible painting, there was another painting. So it had been painted over. And so terahertz radiation is able to uncover that. Okay, so there are a few more things that you can do with that second order polarization. I'm going to flash an equation very quickly. Don't worry about it too much. Yeah. What happens if I send in two frequencies instead of just one? Well, a little trigonometric identity says cos omega 1 cos omega 2, you'll get omega 1 plus omega 2 and omega 1 minus omega 2. So you can get some frequency generation as well as difference frequency generation. And this is something also that Peter Franken and his co-workers demonstrated here in 1962. So you send in omega 1 plus omega 2 and you get omega 3. One application of this phenomenon is to actually generate third harmonics. Now, how do we do that? Well, suppose you come in with frequency omega and you double the frequency using this green second harmonic generation crystal, so you get 2 omega out. At the same time, some of the red comes out. In fact, a lot of it comes out. You don't convert 100% to the second harmonic. So now, you can add them together using some frequency generation in the second crystal, and omega plus 2 omega, you get 3 omega. So you've used that second order process twice, and you get the third harmonic, which is the upper ultraviolet. So you start with, say, 1053 nanometers in the infrared, and you get 351 nanometers in the ultraviolet. Well, this is very important because it lies at the heart of the National Ignition Facility in Lawrence, Livermore. And let's see how, I'll show you a short video about the National Ignition Facility where they're hoping to get laser fusion. Sorry, yeah, they want to get laser fusion. Still. Okay, so, hope this plays. Sound?
Stars. In these stellar cauldrons, hydrogen nuclei are fused together to form helium nuclei, releasing energy that lights the heavens. Can we build the technology to harness this awesome energy on Earth? As we approach our planet, that is exactly what's happening today. Far beneath these clouds lies the National Ignition Facility, located at Lawrence Livermore National Laboratory in Livermore, California. This facility has been built to bring star power to Earth. It is the world's largest and highest energy laser system. Containing 192 laser beams, NIF will explore controlled nuclear fusion to ensure global security, enable sustainable clean energy, and advance our understanding of the universe. 85 feet tall, the laser and target area building is the size of 3 football fields. Inside are 2 parallel laser bays, each containing 96 beam lines. In this animation, which is millions of times slower than real time, we will follow the process for creating a miniature star in the target chamber
infrared beams
by riding along with some of the laser beams. The process.
Oops. Oops.
In total, the energy of the laser beams is increased a quadrillion times as they travel more than 1,500 meters from the master oscillator room to the target chamber. In the switch yard, the parallel bundles of beams are rearranged into a conical configuration. That's so they can be focused into the center of the target chamber and onto the target assembly. The assembly holds the spherical fuel pellet containing hydrogen. Here you see the 8 beams split into 2 groups of 4 beams each, one group traveling up and the other traveling down, heading for equidistant entry ports on the target chamber. Finally, the beams pass through the final optics assemblies, which convert the original infrared laser light to ultraviolet.
So that's where the nonlinear optics happens. You convert all that infrared.
The beams then converge on the 10mm target assembly called the hole run, generating a bath of X-rays.
Now,
this causes the tiny target sphere to implode and ignite in a controlled, self-sustaining fusion reaction.
So you need ultraviolet light to efficiently drive that reaction. Okay, you need very short wavelength. That's a 351 nanometer wavelength. Now this, so here's a picture of the target chamber. And here are the crystals, the KDP crystals that are used for frequency conversion. They are mammoth, but these are sliced into the appropriate sizes of about 40 centimeters by 40 centimeters on the side, and a thickness of about 11 millimeters, and that's what goes into the system. So here we have the second harmonic is done here, and then the third harmonic is done there. And it's all focused into the target chamber. They've been able to get 2 million joules of ultraviolet light from this mammoth laser system. And so hopefully one day we can use it for laser fusion. All right, so let me see how I'm doing on time. We had mentioned photons before. Now, it's possible to have a quantum picture of second harmonic generation using photons. So you send in a photon, 2 photons here are interacting with the medium, and out comes a photon at twice the frequency. Since I'm running short on time, I'm going to skip a whole bunch of things and get to the intensity-dependent refractive index, because that's a very important, another very important aspect of nonlinear optics. So, well, I think I should just mention this one. In the quantum picture, a strong wave that we call a pump photon can break up into 2, a signal and an idler photon, such that their frequencies add up to get the pump frequency. Now, there's literally an infinite number of ways in which you can get 2 of these to add up to get that one frequency. It's like I give you $100 and I say split it up 2 ways between 2 people. You can give one person $1 and that person 99. You can do it 50-50. You can give one, 45, the 55. So there's a lot of ways you can split them. Now, these photons, they satisfy the conservation of energy, but they also have to satisfy conservation of momentum. And it's that conservation of momentum that helps to select which particular pair of photons will be seen in this interaction. And so we can actually build a tunable device called an optical parametric oscillator, where you place the nonlinear crystal between two mirrors, send in the strong pump beam, which is the blue. It breaks up into two photons, the signal and the idler photon. They bounce back and forth, deriving energy from the strong pump beam, and they eventually come out. And so you've created something like a laser, but it's not a laser because you don't have real absorption. You just have these photons breaking up into signal and idler. And so you have a tunable source. Since the frequencies that come out are determined by phase matching, you can tune the output by just varying the angle of your crystal. So here on the next slide, we have the tuning curve, which shows signal frequency, idler frequency, as we vary the phase matching angle. So as you tune the angle, you get these pairs of frequencies that come out. Okay, and you can tune, as you can see, all the way from, say, 400 nanometers to about 3,000 nanometers. So very tunable laser. Okay, so some names. Shortly after Franken demonstrated second harmonic generation, Nicholas Bloombergen, working at Harvard, along with his colleagues Armstrong, Ducoin, and Péchard, published a seminal paper that codified the theory of nonlinear optics. It's a very influential paper, and people refer to it as ABDP, for the initials of the authors. Bloombergen shared the Nobel Prize in '81 for his contributions to nonlinear spectroscopy. Now, a few words about, and then Franken actually left the field in 1963. He figured he'd done it all. He had seen second harmonic generation, he'd seen optical rectification, he had seen some frequency generation, so he left to study other things. But other people pressed on. Now let's take a quick look at some third-order phenomena where we look at the third-order polarization. It's proportional to the electric field cubed. And this can happen in all materials regardless of their symmetry. You don't need non-centrosymmetric materials. So if you send in light like that, quickly, you'll get these two. There's a third harmonic generation here, and there's something that oscillates at the same frequency as the input. It is this term that gives rise to the intensity-dependent refractive index. This is third harmonic generation imaging, where an intense infrared beam is used to image biological samples, which don't have, which are not asymmetric. These are, they're not collagen fibers. The thing glows blue. The intensity-dependent refractive index is also known as the Kerr effect, named after John Kerr, who discovered in 1875 that an applied DC electric field can change the refractive index of a medium. We now know that an intense the intense light wave, the electric field of that wave can also change the refractive index of a medium. And let's look at some applications of that effect. So, in linear optics, we can focus a beam by using a lens. Right? It goes through this thick medium and gets focused. In nonlinear optics, suppose we send in light whose intensity distribution looks like this. So the light is going this way, and it's most intense in the middle, and it falls off the sides. When this light enters the material, it will change the refractive index in proportion to the intensity. And so this material becomes denser in the middle than on the sides. So it will act like a lens. So in a lens, the light is bending towards the denser regions. So here, the light focuses upon itself. It's called self-focusing. Now, this self-focusing can be catastrophic. An intense beam can focus to a point such that it can destroy the material. So that's actually a problem in laser amplifiers because self-focusing can make holes in your amplifier. That's the problem that Gerard Mourou and Donna Strickland solved. They wanted to get rid of this self-focusing because it was blowing up their amplifiers. So that's what they did. They took a pulse that they wanted to amplify. They stretched the pulse so that it wasn't so intense anymore. And then they amplified it. Here's the amplified pulse, amplified and stretched. Then they compressed it. They compressed it to get this very, very intense pulse. That would have probably destroyed the amplifier. So by stretching it and lowering the energy before you sent it in, lowering the peak power, you can now amplify it. So for this work, they were awarded the Nobel Prize last year. And you'll be hearing Donna Strickland on the 30th. Okay, we'll talk about one last application, which is the generation of short pulses from Kerr lens mode locking. What's mode locking? Well, mode locking is where you get, this will go a little bit fast, so it's okay if you don't completely grasp it. So in a laser, you have many different modes, yeah? And ordinarily, they don't have a fixed phase relationship to each other, and so they add up constructively and destructively, and you get out something not very intense. If all the modes line up in phase, you can get a sharp pulse. So you get a string of sharp pulses. Well, one way to do that is to use this self-focusing effect. So here we have a laser. There'll be mirrors here and there. Here's your Thai sapphire medium that provides gain. Now, at low intensity, the dotted line here shows that the beam spreads. So because of diffraction, right? Spreading. And it can be blocked by this slit over here. So much of the light is blocked if the intensity is low. If the intensity is high, self-focusing occurs, and that's shown in the red beam. So it's self-focused, and it can escape through the slit. So intense light is able to dig itself out of the cavity, and it comes out, boom, in a pulse. So let me show you a cartoon. So it's like squeezing a tube of toothpaste. You squeeze it, and you give an energy to it, and it's able to escape through that small exit there. Okay, so that's Kerr-Lens mode locking. Now, it was discovered by accident. This laser suddenly there spontaneously began to pulse like this. It was called magic mode locking when it was first discovered because there was no obvious mechanism. But eventually it was all figured out that that's what's going on. It's self-focusing. Okay, so I think that I've used up my time mostly, so but there's a lot more that I could show you about the amazing life of nonlinear optics, including frequency combs, supercontinuum generation, and one application of these very short pulses from mode locking, these femtosecond pulses that you get from mode locking. One application which was discovered right here in Michigan by Jamuru and his group was applying femtosecond pulses for eye surgery. They saw that for very short pulses, the damage, you can make a very fine, lines here compared to long pulses. Long nanosecond pulses will just cause a lot of heating and damage, whereas with short femtosecond pulses, there's very limited damage. And so now you get femtosecond LASIK, based on mode locking. Okay, so to wrap up, that event that occurred in Randall Lab in 1961 led to truly some amazing applications over the years. It's unfortunate that Peter Franken, well, I personally think it's unfortunate that he never got the Nobel Prize for this work that gave birth to so many fields. Now we have things like high harmonic generation, which you get when you use intensities of the order like 10 to the 14 watts per square centimeter. You can generate harmonics all the way up to the 200th harmonic and beyond. Now, the physics of that is quite different from the physics of the low-order harmonics. For the low-order harmonics, we were still dealing with bound electrons. The electrons never escaped from their atom. For high harmonic generation, the electrons actually driven out of the atom. They get accelerated back and smash into the nucleus. And during that smashing and recombining, they emit these very high harmonics, the 200th harmonic. I've heard that there's been a 4,000th harmonic. When you start getting like 100th harmonic, 200th harmonic, you get into the X-rays. So now nonlinear optics allows you to get into the X-ray region using just a tabletop laser. And those intense lasers were enabled by chirp pulse amplification. I mentioned the Nobel Prize, yeah? And so in trying to avoid nonlinearity, they invented chirp pulse amplification, which then allowed us to get to even higher intensities, to create even more nonlinear effects, extreme nonlinear effects like high harmonic generation, and create attosecond pulses of order 10 to minus 18 seconds. One of Gerard Mourou's dreams is to eventually create lasers so intense that the quantum vacuum itself will exhibit nonlinearity. So you send these incredibly intense beams into the vacuum, and you can create particles. Matter and antimatter will emerge just by driving them with very intense light. So to conclude, let me pay homage to Peter Franken again. So I mentioned that he left the field after a few years. But he would only work on something so long as he was passionate about it. And this is slightly, I guess, PG-13 or something. So he went off to consummate other events after his work on nonlinear optics. So he passed away in '99, and was a great person, really great. He served on the faculty here for many years, and then he moved to Arizona, where he directed the Center for the Optical Sciences Center. So anyway, thank you for your attention, and I hope you took a few things away from this presentation.